Of all the topics covered in this playlist, factoring polynomials is probably the most important one. And if you didn't watch my previous video on polynomials, and you don't have any background knowledge to polynomials, I recommend go checking it out. Now, before we get to what's on screen, let's take a bit of time to know what factoring really is. Factoring is just the process by which we go about determining what we multiply to get a given quantity. So for instance, there's many ways to factor out the number 12. That's to say that there's many ways to multiply things together to get the number 12. So for example, 2 times 6, 1/2 times 24, 3 times 4, and -2 and -6. Now, a common method of factorizing numbers is to completely factor the numbers into only positive prime numbers. Now, a prime number is just a number whose only positive factors are 1 in itself. So for example, 2, 3, 5, and 7. Now these are all prime numbers, since the only positive factors of 2 are 2 and 1. Same for 3, it's 3 and 1, 5, 5 and 1, 7, 7. Now some numbers that wouldn't be prime numbers would be 4, 6, and 10, since you can multiply 2 and 2 to get 4 rather than just only 4 and 1. And same with 6, you can do 3 and 2 to get 6, and for 10, of course, you can do 5 and 2 to get 10. Now, if we completely factor a number into only positive prime factors, there will only be one way of doing it, and that's why people do this. So for example, the complete factorization for 12 is 2 times 2 times 3. This is the only way we can do it with positive prime factors. And if you don't believe me, you can try yourself. Try to factor out 12 with only positive prime factors. You'll quickly notice that this is the only possible way. The factoring polynomials is done in pretty much the same form, where we determine all the terms that were multiplied together to get the given polynomial. And then we try to factor out all the terms we found in the first step, and this process continues until we can't do so anymore. And as mentioned before, when we can't do it anymore, we'll say that it's completely factored. So take the first example in yellow. X squared minus 16 can be factored out into two binomials, x plus 4 and x minus 4. And this is completely factored, since neither of the two factors on the right-hand side can be further factored. Whereas take the example in orange, x to the power of 4 minus 16 can be factored out into two binomials, x squared plus 4 and x squared minus 4. And notice that x squared minus 4 can be further factored. So while this is a factorization of the polynomial, it's not completely factored. And so its completely factored form is x squared plus 4 times x plus 2 times x minus 2, all in binomial form. Now let's remember from our previous video on polynomials that the distributive law states that a times the quantity of the sum b of c can be rewritten as the sum of b and c multiplied with coefficients of a. And we're going to keep this in mind for our first factoring method, which is factoring out the greatest common factor, otherwise known as the GCF. And in factoring out the GCF, we notice that each term has a coefficient in it, and so we can factor it out using the converse statement of the distributive law, which would just be that a times b plus a times c is a times the quantity of b plus c. So for a, the GCF is 2x squared. So using the converse of the distributive law, we can write this as 2x squared over a quantity of something. Now to fill in that quantity, all we have to do is take each term and divide it by 2x squared. So we get 4x squared, since 8x to the power of 4 divided by 2x to the power of 2 is 4x squared. And then we get minus 2x, since negative 4x cubed divided by 2x squared is negative 2x. And then we get a constant 5, since 10x squared divided by 2x squared is just 5. Now for b, we're introducing two variables. However, the same idea persists. Now we notice that each term at most contains an x cubed and a y. So we can already write this as x cubed times y over a given quantity. And now to fill in that quantity once again, we're going to look at each term and divide it by the GCF. So first we're going to get y, since x cubed times y divided by x cubed times y squared is just y. And then walking through left to right, we're going to get 3x. And then we're going to get 5x to the power of 2 times y squared. Now we're going to be taking a look at another method called factor by grouping. And while this method isn't used all that much, it can still sometimes be somewhat useful. And the best way to illustrate this is through a few examples. So in this case, what we're looking to do is group the first two terms together, 3x squared and negative 2x, and then group the last two terms together, 12x and negative 8. So all that's going to look like is just putting them together in parentheses. And I'll notice that in these two binomial forms, we can already factor them out. So in the first binomial, there's a factor of x, so we can factor it out as x. And then inside the quantity, again, we're looking to divide all the terms by that factor. So we have 3x squared divided by x, which is 3x. And then negative 2x divided by x is negative 2. Now for our second binomial, we can see that there's a factor of 4. So we can write this over the quantity, and 12x divided by 4 is 3x, and then negative 8 divided by 4 is negative 2. Now you've noticed that inside the brackets, 3x minus 2 has repeated, and now using an extended version of our distributive property, which we can write as a times p plus q plus b times p plus q equals a plus b times p plus q. So for us, that means we can write this as x plus 4 times 3x minus 2. And that's it completely factored. Now for b, we're going to do the same initial step, but this time notice that the final two terms are negative, and so we can already factor out the negative sign for our second binomial. So doing this gives us x to the power 5 plus x minus 2x to the power 4 plus 2. And so we should be able to spot with the first binomial that there's a factor of x, so we can factor that out. And then inside the quantity, again, we're just dividing the terms. So we get x to the power 4 plus 1. Now for our second binomial, we can keep the negative sign, and notice that there's a factor of 2. So we can write that outside our quantity. And then inside again, same idea. It's going to be x to the power 4 plus 1. And using our distributive property, we'll get x minus 2, and then x to the power 4 plus 1, given that our quantities are the same sum. And that also acts as a good way to verify that you've done the steps correctly. Now we're back to where we were before, and we're going to be taking a look at quadratic polynomials. Note that a quadratic is just another term for a second degree polynomial, aka a polynomial with a degree of 2. And for the problems I'm going to give you in this section, we're going to be attempting to factor out quadratic polynomials into two first degree polynomials, and henceforth linear polynomials. Now let's take a look at some examples where we're going to factor out each of the following polynomials. Now since our first term is x squared, we know that we can write this as x plus something multiplied by x plus something. And we get this from our special products in our previous video on polynomials. And now to start filling in these quadratics with a coefficient of 1 on the x squared term, which are also called monoquadratics, the general rule is that x squared plus bx plus c can be written as x plus m times x plus n, where m and n need to satisfy a sum of b and a product of c. Or in other words, we're looking for two numbers that fill in these spots that when multiplied together, we'll get our constant term, and when added together, we'll get our coefficient of our middle term. And again, this comes from our distributive property. Now we can narrow down the possibilities for m and n considerably by looking at the factors of negative 15. Now for monoquadratics, again, remember the rule requires that the pair of factors we found need to add up to our middle term coefficient, which is 2. So the pair here that adds up to 2 is 5 and negative 3. And so we can fill that in our blank spot. So we'll get negative 3 and 5. And that comes out to be x minus 3 multiplied by x plus 5. Now again, we're looking at a monoquadratic where the coefficient of the x squared term is 1. So we can already write this as x plus something multiplied by x plus something. Now to fill in these spots, again, we're looking for two numbers that when multiplied get 24, and then when added get negative 10. Now we can take a look at our middle term coefficient sign and our constant symbol sign. We said our middle term coefficient sign is negative, and our constant term is positive. So this tells us that the factor pair we're looking for is going to have both negative values, since two negatives when multiplied make a positive, and then when summing, it's going to have to give some kind of negative value. That's going to help narrow down our possible factor pairs. So let's try negative 2, negative 12. Well, negative 2 minus 12 is negative 14, so that's not going to work. Now let's try negative 8 and negative 3. So while negative 8 and negative 3 when multiplied make 24, just like our previous pair, when added together, we don't get negative 10. So we have to try again. Let's try negative 4 and negative 6. Now negative 4 minus 6 does in fact equal 10. So these are going to be the values we're looking for in the blank spaces. So we can write this as negative 4 and negative 6. And then we write that as x minus 4 times x minus 6. And there we go. There's some nice special forms of polynomials that can make factoring way easier on occasion. So I'm going to give you 5 to try and memorize, since we're going to apply them through some worked examples. And you may even recognize the first 3 from our previous video on polynomials. So I've given you 3 examples here, and I'm going to leave the formulas on the right side of the screen, so you can look to them to see which of these have a corresponding special formula. So feel free to pause the video if need be. Now for a, in this case, we have 3 terms, and it's a monoquadratic polynomial. Notice as well that the constant is a perfect square, which just means that it can be expressed as being multiplied by itself, and it's a square root of 10. Notice as well that 2 times 10 is the coefficient of the middle term with a different sign. So it looks like we're going to be using our second special form right here. So if we just plug in the values, we're going to get x minus 10 squared. And to be clear, you probably could have used the general process for factoring these monoquadratic polynomials, but over time, if you try to master these special forms, they can become very handy and save you a lot of time. Now for b, we need to notice that we have a difference of perfect squares. So we can rewrite this as 5x all to the power of 2 minus 3 to the power of 2. Now we should spot that this corresponds to our third special form, which is a squared minus b squared, is a plus b times a minus b. So then we can just write that as 5x plus 3 times 5x minus 3. Now for c, it's the same thing, but we have a case of perfect cubes. So we can write this as 2x all to the power of 3, and then 1. If we put it to the power of 3, it's never going to change. Or if we put it to the power of any positive integer, it's not going to change. So of course we can write this as 1 cubed. And now in this form, we should see that it corresponds to our fourth special case. And so knowing a and b, we can write it in this form. So we'll get 2x plus 1 multiplied by 4x squared minus 2x plus 1. Now let's look at factoring polynomials with a degree greater than 2 and where our coefficient for the greatest exponent term is possibly greater than 1. Now there's not really a general method for doing these types of polynomials, but I chose for each one that we can try to cover a different method according to the question we're tackling. So you should notice that for question A, each term has a GCF of 3x squared. So like before, we can then write 3x squared all around a quantity, and now we're just going to divide each of the terms by this value that's outside the quantity. So we get x squared minus x minus 12. You should notice that what's left inside the quantity is a standard monoquadratic, and now we can repeat the techniques that we had previously. So we need two numbers when multiplied together should get us negative 12, and then when added should get us negative 1. So if you need to, you can write out all the factors for negative 12, but I already know it's negative 4 and 3, so I'm just going to write that down. And remember that for this step, we need to make sure that the value outside of the quantity needs to be the GCF and not just some common factor. Now for b, we don't have a GCF, but we should notice that it's the difference of perfect squares. So we can write this as x squared to the power of 2 minus 5 to the power of 2. Now if you can remember it, we're going to use our third special form, which I'll put on the right here for you. And so we're going to get x squared plus 5 times x squared minus 5. And either of the remaining binomials can be further factorized, so we're done here. Now for c, let's start off by factoring a different polynomial. So let's take u squared plus u minus 20. And now this is a monoquadratic. When we factorize it, we should get u minus 4 times u plus 5. And we just used a different variable u because x was already used in the original polynomial. You might be asking, why would we do this at all? Well, think about it this way. We can do a special trick. If we let u equal x squared, then u squared becomes x squared to the power of 2. And that equals x to the power of 4. And so now we know that x to the power of 4 plus x to the power of 2 minus 20 is equal to u squared plus u minus 20. And as shown here, we already know how to factorize the right-hand side. So now what we can do is we can just substitute u for x squared as per our definition. So that'll give us x squared minus 4 multiplied by x squared plus 5. And now we're left with two binomials, but notice that the left binomial can be further factorized. So let's do that. We'll give us x minus 2 times x plus 2 times x squared plus 5. And that's our answer. Now for our next video, we're going to be taking a look at rational expressions.